Hello, good people. Today we are going to look at static routing. This is the first of the series of routing we are going to do for Huawei routers. We have realized people are suffering. There are no good materials. We decided to do something from our end and see whether we can help a person or two. So we are going to look at Huawei Routing Series. We are going to use VRP version 5. VRP is Versatile Routing Platform. Is the iOS for Huawei routers. So in our agenda today, we are going to look at basic static routing, and then we'll talk about how to optimize static routing using preference and bidirectional forward detection. Pay attention to that one, is very interesting, has a very practical applicability. So let's get started. Once you realize that when networks grows, you introduce routers so that you can split your network into smaller sub-networks. So the challenge when you do that, the challenge remains that if computers are in the same network, they'll be able to send data to each other because through the switch, through MAC address forwarding in the switch. But what happens when a PC in one network wants to send data into a PC in another network? For example, PC1 wants to communicate with PC3. So the first thing a computer does when it wants to forward data is there's encapsulation. So data is encapsulated in all layers of the OSI. And in this case, because we're looking at layer 3, we look at how data is encapsulated at layer 3. So when data is coming from PC1, at layer 3, it's encapsulated with, among other things, the destination IP address, which is this PC, and the source IP address. When the PC sees that the destination IP address is not within the network that I am in, it forwards that data to the default gateway. So the data will be forwarded to the default gateway, and the default gateway is router A. Then what will router A do when it receives this data? It does the opposite of encapsulation. It decapsulates up to layer 3. A router is a layer 3 device, will decapsulate up to layer 3 and see the destination IP address. Then it will look at its routing table and see whether it has a path to this destination IP address. So two things will happen. One, if value to the destination exists in the routing table, the data will be forwarded to the next hop as specified in the route entry. If there is a route to that destination, it will be forwarded according to the route entry, and the route entry will contain the next hop. And the next hop must first be reachable. If the next hop is not reachable, it will not be forwarded. The data will not be forwarded. But what happens if there is no destination, if there's no path to the destination in the routing table, the data will be dropped. If there is no route to the destination IP, the data will be dropped. So what we have to do is, before we know that whether this router A will be able to forward data to this particular network, we have to go into router A and see whether the route to that destination IP exists in the routing table. So there's a command for doing that in Huawei, and it's this command, display IP routing table. This one will show us all the routes that are contained in the router. So before you configure any routes, by default, you'll only see direct routes. Direct routes are the attached routes, the attached interfaces, the IP addresses. Those networks are the only ones that you will see before you configure any route. I have seen some questions in Huawei exam where they ask, by default, what routes are contained in the routing table of the router? It's by the direct routes only, the ones that are directly attached to the router. So by default, the router only knows about the directly connected routes, which are designated as direct under protocol. So as you can see, this router only knows about this directly connected network and this network of 192.168.1.0. it doesn't know about this one, which is not attached direct to it. It's not attached directly to it. So it doesn't know about this network. So because it doesn't know data, if you try to ping from, sorry about this, it didn't start our, we are using a simulator called ENSP. This one is from Huawei. Just like Packet Tracer, you can look for it on the internet. So a ping from PC1 to PC through that PC3 does not go through because the router does not have the network to that particular destination IP address. Sorry. So we don't expect ping to go through from PC1 to PC3, and that's what the output shows here, that ping from 192.168.1.2 to 192.168.2.2 do not go through, because when traffic comes to router A, the router A sees that it doesn't have a route to that particular destination and drops the traffic. So let's get our router started here. So we should have done this before. So wait for our devices to, they're coming up. The routers are taking a bit of time to come up. Yeah, thank God we are here. So if we come here and we use that command for display IP routing table, you will see that we only have network 10.10.10, this network 10.10 and 10.10 and 192.168, this network. We do not have for 192.168.2. So you only have the directly connected routes. So here, when you try to ping, from here you ping 192.168.2.2, we are not supposed, we're having a timeout. And if you trace, we can try to trace and see where we are getting timed out. You can see we are getting timed at the default gateway, because after the data hits the default gateway, the router does not have the route to the destination IP address, so the data is dropped. So what do? We need to add more routes. We need to add more routes into the routing table of router A so that it's able to forward data appropriately. So we need to add routes, to inject routes into the routing table of router A. So how do we inject routes? We can inject routes using the following methods. We have static method, all dynamic method, dynamic routing protocols. So first of them, we have OSPF, we have RIP, we have intermediary system to intermediary systems, and we have border gateway protocol. We will have a series of routing where we'll go through all of them. So today we are starting with the static method. So to configure static method is quite straightforward. You just need some parameters, and one of those parameters is that you need to know the network whose route is missing in the routing table. In our case, you want to route for this machine. We want to route for this machine. This is our destination. So we need the network IP for this particular IP address. And how do you work out the network IP? You do some subnetting using that IP address and the subnet mask. So for this, the network will be 192.168.2.0. If you would want us to cover IP subnetting in future, you can give us a comment below. We can cover that one for your benefit, but you'll use now the subnet and the IP address to work out the network IP. You'll need the network IP. The next thing you'll need is the next hop to that particular network. So if I'm coming from router A here, if I'm coming from router A and I want to go to this network, which is my next hop? My next hop is this IP. So you need to know the next IP address. So, and that next IP address must be reachable. So you have to, when you know your IP, my next hop IP address, you must ping it first to see that it's reachable. Then after you have done that, so here is what we are talking about. If you have the network, we want to route for this network, we want to add this network. What is the next hop to this network? It's this 10.10.10.2. So first of all, we have to establish that that particular IP is reachable. And then after you have done that, now you can use the command IP route static network IP, the mask and the next hop. So IP route static, we are looking for this particular network, 192.168.2.0, and the mask is 24, and the next hop is 10.10.10.2. So we can do that. We come to our router A. Let me clear this first. We go to system. We say IP route static 192.168.2.0, not .1, it's .0 because we are looking for the network IP. But first of all, we have to test whether the next hop is reachable. We have said 10.10. We are from here. If we see here, our next hop is this .2 and this .1. So 10.10.10.2 is our next hop. .2, you can see it's reachable. So we can now construct the route, IP route static 192.168.2.0 24 10.10.10.2. So now if you display IP, let me clear this so that it will be visible for you. If now we check what we have in the routing table, we should be able to see now a route that is not direct. So now we have created a static route. So it tells us the static route. We'll talk about this number later. It's called preference. It tells us the preference is 60 for that route. So the default preference for Huawei static routes is 60. In other, like Cisco, they call this administrative distance. And for static routes in Cisco, it's 1. For Juniper, I think they call it preference as well, but the default value is 5. So let's now try to ping again from our PC1, we try to ping to 2.2. We're still timing out. Why are we timing out? Because of how ISMP works. When I send an ISMP packet here, I expect this machine to give me a response. So when I send data goes through, but when this one wants to send me a reply, it has to send to this router. The question is, does router B know about this network? I doubt so, but we can check because we said a router by default only knows about the directly connected network, only this one and this one. So it doesn't know about this particular network. And if we check display IP routing table, so we only have 192.168.2. We do not have .1. So even on this side, we need to add. When you're coming here, you want to go here. What is the next hop? 10.10.10.1. So first of all, we establish that .1 is reachable. We can ping 10.10.10.1 and it's reachable. So now we can construct a route. So we say IP routing route static 192.168. Again, we do subnetting to get the network IP, and then we indicate the next hop. So now we should expect our data to go through, but it's not going through. Why is it not going through? Display IP routing table. There is a static route here, 1.2. There's also static route 2. 2.2 is pointing to. Should go through. Sorry for troubleshooting on live. Destination host unreachable. Display correct. We need to check whether these machines have been configured. 192.168. Can I pin the gateway? Yeah, that's a problem. Let me fix that gateway. Display IP interface brief. Gateway is up. 2.1. Reachable. Today is reachable. What is happening here? Yes, we're able now to go through. The data now is going through from PC1. This is PC1 to PC3 because we have end-to-end connectivity. So that's simply how you do static routes. It's quite straightforward. All you need to know is the network IP of the network for which you are routing and the next hop. But the next hop has to be reachable. And to ensure whatever you do to one end, you have to do to the other end to ensure an end-to-end connectivity so that you do not have data going on one direction, but on the return path, it's not working. So let's switch gear and talk about optimizing. How to optimize static routes. Let's switch gear and talk about how to optimize static routes using preference and bidirectional forward detection. So let's assume, for example, you have a setup like this where you have two sites and a third one here for introducing a secondary route, such that these two sites are connected to each other, but the path to the network they are connected to, you can reach the network to, to router B through two paths. You can use this path, and also you can use this path. So you have two paths. So in your route, when you start, maybe this one is a slower link, maybe a microwave link, but this one is a fiber connectivity. So this one is a bit faster. Maybe a service provider came later and told you that we are the best in town now, we have the fastest speed. You can contract us. Now they can use a fiber, but here you've been using a microwave, for example. So maybe initially you had configured for you to go to this site, I have to go through site, the back route site, and then I go to site B. Then later you introduce this network. Now we want to see how can we make the new route more preferable over the old route. So let's see from our simulation how we can do that. Let's get these machines, these devices, our devices started. So we'll first configure to reach this network, we first configure this route, because originally maybe we had this route and this one for fiber came later. So we'll configure how to reach this network going through this router, the back route, and the same vice versa. If you are here, you want to reach here, you go through the back route, and then later we will configure the one for fiber. So let's see whether our routers have started. Still starting. Okay. Okay, that one has started. Started as well. This ones have not yet started. At least the devices are coming up. Yeah, fantastic. So here we need to, from here, we configure a route to reach this network using this next hop. So the next hop is 10.10.2.2, and the network is 192. The network is, if you can make this one a bit bigger so that we are able to see everything. How do I make it bigger? So we want to, from here, we want to reach this network 192.168.2.0 because the mask is 24. I can quickly subnet and say this is 2.0. But the next hop, when you're here, the next hop is 10.10.20.2. So the first thing, remember, is to ensure that that next hop is reachable. 10.10.20.2. And we see it's reachable. So now we can construct an IP, a static route going to 192.168.2.0. The mask is 24, 10.10.20.2. See that? Now, you also come here and check, does this one know how to reach to that network? I doubt, because as we said by default, this router will only know about this network and this network. It doesn't know about this network. So even here we have to add that particular network and point to this next hop. Can you see that? So the next hop in that case is we need to ping 10.10.30.2. And we see it's reachable. So we can construct a route. Let's clear this one. We can say IP route static. It's 192, still to the same network. How to, because you're telling this router how to reach this network. So we have 192.168.2.0, 24, and then the next hop is 10.30.2. And again, because of the return traffic, also this router need to know about this network because it doesn't know about this network. So you also need to add 192.168.1.0 quick subnetting and point to this particular next hop, 10.10.20.1. So first thing we do is what? We check whether the next hop is reachable, our desired next hop. And you see it's reachable. So now we can add the route, IP route static 192.168.1.0, 24, and the next hop is 10.10.20.1. So the next part is we come to this router. This router knows about this network, but it doesn't know about this network. We want to make it to add this network into the routing table of B, but going through this particular next hop, 10.10.30.1. So we go to B. And if you display IP route here, routing table, you see there's no 192.168.1. So we need to add that. Before that, let me clear. And then let's ping our next hop. Our next hop should be this, router B. So I mean back route, 10.10.30.1. So the next hop is reachable. So now we can construct the route, IP route static 192.168.1.0. Sorry for the typo. .30.1. Sorry, IP route static. I was missing the mask. 24. So now, if we come here, you try to ping this PC2, we should expect traffic to go through because we have end-to-end connectivity. So let's ping 192.168.2.2 from PC1. It's going through. And which path is it using? We should expect it to come from here. It goes here and finally goes there. So let's trace that. So it goes from 192. Let's trace that and see. It goes from here, hits the gateway 192.168.1, and then goes to 10. This IP address 10.10.2, and then finally goes here 10.10.2.30.2, and finally to the destination. So that is okay. But now, when our service provider, we add in a service provider who comes with a switch. Maybe you're in a building, in a multi-tenant building, where the provider has come with a switch where it connects you, your company, and several other customers. The same thing as a remote site. So there's a provider switch here and there's a provider switch here. But we do not care for the provider switch because it's layer 3, but we need to be careful about it because it will introduce issues later that we look at. So here we can say the same destination, but now instead of using this route, we use this route so that the same destination, but the next hop will be 10.10.2, not 10.20. So we use this. So we configure another route here to the same destination. I don't know whether we're able to follow this. That is the same destination, but using a different route now. So let's check whether the new next hop is reachable, 10.2, and we see it's reachable. Since it's reachable, we can create that new route. 192.168.2.0.24 and put that particular next hop. And what you do to that, to this router, you do to the other router. To this, you do to the other router, so that you have end-to-end connectivity. So we also need to know, to reach this particular network. You also want to reach this particular network using this link. So the next hop will be 10.10.1. So when you go to B, first ping 10.10.10.1 is the next hop. It's reachable. So you can construct a route, IP route static 192.168.1.0, because the subnet is 24. A quick subnetting tells me the IP network IP is .1, going through 10.10.10.1. All right. So now, if you look at the routing table of A, it will have those two routes to the same destination. Same destination, but two different routes. So display IP routing table. You see, the same destination of 192 has two parts. It has two parts. It has two parts. One using 10.10.20.2, one using this, and another one using 10.10.10.2. The other one using this path. So if we trace from here, let's see which path will be used. So it uses the one for 20.2. It's using 20.2. This one is still using this one. It has not chosen this one. So now we want to force it to use this one. What do? We work with preference. By default, when you configure static routes for Cisco switch, for Huawei switches, the default preference is 60. So if you want one route to be preferred over the other, you lower its preference. So I want it to prefer this route. So I can make this preference for this route lower than the default one, because the one I don't prefer will have 60. The one I prefer, I can make its preference lower. That's how preference works. The lower the value, the more preferred it is. It's like golf. When you have lower values, you are the winner. So let's see how to do that. So we had a route here. We constructed this route. If you question mark this route, you'll see there's a value called preference. So we can add preference here and say, make this preference 50, for example. And we are saying they have succeeded in modifying. So now if we display routing table, you will see now we only have one route, because this route has the lower preference. The other route that had 60, it lies in waiting. It's called a floating route. It lies in waiting. It only comes up when this one disappears from the routing table. It will come up when this one disappears from the routing table. So whatever we do to router A, we do to router B. So in router B, we had that route we created. So because we prefer this one, we can give it a preference value of 50 as well. Sorry, my preference is misspelled. Preference of 50. So if you display IP routing table here, you'll still get there's only one route here. So now if we ping, first of all, we make sure that the pings are still going through. Pings are not going through. We have timed out. Now they are going through. But which path is it using? You can check the path. You see now it's using, it goes to the gateway and then to 10.2. It's using this path. Right together? That's how you influence the route that the router installs in the routing table using preference. So let's have some. So that's what you're talking about, preference. By default, the preference of static routes in Huawei is 60. And if you want one static route to be preferred over the other, you make the preference of the preferred route lower than the other route, not router route. There's a miss. So this is how you change the preference. Now we have another problem. When you have a setup like this, if this interface goes down, the router will note that it has gone down and remove this route from the routing table. So let's try to simulate that. So you see this route is, so if for example, we simulate a failure on that particular interface, the preferred interface, we simulate a failure by shutting it. Let's see what we'll have in the routing table. You see it has been removed from the routing table. It has been removed from the routing table, and the one that was floating, the one was lying in waiting, has been installed. That is good because this router can detect a failure here. So supposing, let's remove that. Let's return it the way it was, and we clear this. What if there is a failure within the service provider environment? This router will never know that there's a failure within the service provider environment. Let's try to simulate that as well. We simulate a failure in the service provider environment. So I know that interface is 0/0/2. Let's shut. And there's a now failure here. If you look at the routing table here, you still have it preferring that route. So traffic will come, and this one will think I should forward it to this destination. But as I'm forwarding, traffic will be dropped here. Will be dropped here because this router has no way of knowing that this one has failed, so that I can remove it from the routing table like I did when this one went down. Because I can tell this one went down, the router can tell this one went down, but it cannot tell that this went down. So what do? We introduce something called tracking. So tracking, that's what we wanted to talk about. So when there's failure within the service provider environment, the router does not know that there is a failure here, so that it can remove that route from the routing table. So we introduce tracking. And tracking simply means you configure a BFD. We'll talk in this series, we'll also talk about BFD, bidirectional forward detection, so that we can detect failures very fast. So we'll configure BFD. I'll quickly configure BFD. In later session, do not worry about the commands I'll use. In later sessions, we'll go through the details of how BFD works. For now, let's just configure BFD. Then I'll show you how we can use tracking to detect failure within such environment, whereby the router does not have a way of knowing that the remote network has gone down. So let's have our BFD. So this is how you configure the BFD. First, you enable it, and then you BFD, we give it a name. You can call it monitor static. monitor, we bind PIP, we say PIP. We need to monitor this IP address 10.10.2. 10.10.10.2, and then the interface, it goes through, to go to that interface, we go through G0/0/0, and then discriminator, there's something called discriminator local, it's 1, discriminator remote, call it 2, and then commit. So what we do here, we also do the other side. So you enable BFD first, quit, and then BFD, give it a name of monitor static, and then PIP, bind, sorry, bind PIP. We want on this side, we want to monitor this IP address 10.10.1. So 10.10.10.1, and then interface. Here, you're also going to 0.0.0, and then local discriminator local, discriminator local 2, discriminator remote 1, and we can check whether our session is up. We check display BFD session, or display BFD session on, it's still not up. A commit, we did commit. It's down because we need to, here we issued the shut command, we need to undo shut. Let's see whether our session is up. Still down. Still down because the route has not come up. Let's see. Still down. Display BFD sessions all. Yeah, it should now be up. Yeah, it's up now. Now, what you need to do is to make our router, our static route, follow the status of the BFD session. If the BFD session is up, the route will be up. If the BFD session is down, the route will go down and be removed from the routing table. So that's what we call tracking. So we will be tracking the status of the BFD session. So here, remember that route we configured, we can make that route track that session. So this route we had here, it's not there. So let's display current. We see what that route we have configured. So this route we can have configured here, we can make it track that BFD session. So we can copy this before we paste, we clear. And then we paste. Then if you question mark, you can see there's track command. So we can track, we track. And what are we tracking? See, one of the things we can track is a BFD session. So BFD session. BFD session. So before we track, let's simulate failure before we track. Supposing now there was a failure here in the service provider environment, we see now there is a failure. So if you try to ping from here, your traffic will be dropped because this router still thinks I can forward traffic here because that route still exists in the routing table. If you display routing table here, you see the route still exists, even though there is a failure. There is a layer 2 and layer 1 failure within the service provider environment. So now, to avoid that problem, that's why we are using tracking. So we can track. So if we paste our, let's now do our track and see what happens. So if we paste, we can tell this one to track the BFD session, and we call it monitor static. So we have succeeded. What you do to this router, you do it to router B as well. So quit here. This. Do we have that route? Yeah, we have it here. So we can track also this one. And we track BFD. Also here we called it monitor static. So let's bring back our service provider. So our service provider now is up. Everything is working well. We have our service provider is up. So if I ping, I should go through. And if I trace, I should go through the preferred link, which is .10. Okay, still not picked up. Let's wait for it to pick up. Display IP routing table. So still for 60, we need to wait a bit. We're still tracking. Yeah, now that one has come up. So we should go through the best route, which is this route. So let's trace that. It's going 10.2. Now the problem when this was going down, we still had it. We still had traffic. We had traffic being dropped. So right now, let's shut it. Let's simulate a failure again. So now there is a failure, but I should still go through. Ping still go through. And you can see the path it uses. Now it uses the backup path. 10.10.20.2. It uses 10.10.20.2. Just because we had a track on this. And when it comes up, we expect it to resume. So let's remove, let's say the service provider has repaired the fault. Now it will, though it will wait for the, if you display BFD sessions here, display BFD session. Oh. So it's still down until it comes up. That's when we'll have that router installed. So as you can see right now, display IP routing table. The backup route is the one that still exists, waiting for the BFD session to come up. Because we are tracking, we are following the status of the BFD session. You can see now from this output is that the BFD session has come up. The BFD session has come up. Now, if we display IP routing table, we will see now the preferred route is on the one that has been installed on the routing table because it's now up. The BFD session is up, so the route will be installed in the routing table. If the BFD session was down, the IP will be removed. The route will be removed from the routing table. So that's all we need to know about BFD. That's all we need to know about BFD. So in such a case, this router has no method of knowing that this particular link has gone down. So we use a BFD session, we create a BFD session, and then we track it. So this is how you create a BFD session, and then we track it. You track the BFD session. Follow the status of the BFD session. If the BFD session is down, this route will be removed from the routing table. If it's up, it will be installed back into the routing table. So before we end this session, we want to compare the preference for different vendors, because you guys might be working in a multi-vendor environment, and you might sometimes you might find some routing issues if your values do not match. So in Huawei, it's called preference, and the default value is 60. In Cisco, the same, it's called administrative distance. Administrative distance, and the default value is 1. For Juniper, it's also called preference, it's 5. Even for those other vendors, the principle is the same. The lower the preference or the lower the administrative distance, the more preferred the route is. So it doesn't change. It doesn't change, but it's good you know the default value so that in your mixed environment, you can set up one value for all of them so that you do not have some suboptimal routing. So that was all for today. We will be having a series of routing. So the next release will be on OSPF. Please, if you like the video, hit that like button, subscribe, and hit the notification bell so that when we proceed this next video, you'll be able to be notified. Thank you very much. I hope this one has helped in your work, or if you're preparing for an exam, you have gathered some pointers, or if you wanted to refresh your knowledge. Thank you and stay tuned.